thank you for inviting me to your fascinating meeting already. I'm I'm learning so much. While I was waiting, I was just Googling what are the California bears, and so I learned all about grizzly bears, and then I learned all about the Californian landscape, and then I learned all about an athletics team. So yeah, go Bears! That was worth it for me already. Yeah, so I mean, what an interesting talk this is going to be because I sat down and looked and I was like, right, I'll give my usual 40-minute book, buy my book spiel. And then I was like, oh, it's 20 minutes. Right. Okay. How on earth am I going to squish the universe into 20 minutes? Like, right. Okay. And one of your starting quotes was quite wonderful, which is just be truthful and just live your life honestly, and this will all be good. So I have great respect for your club getting together so early to learn, because that's how I feel. I eat my cornflakes with my New Scientist, which is like Scientific American. That's my news for the morning. I don't like looking at the real news because it makes me sad in the morning, so I just read my science. And I took the week off this week. Let me just see if I can just share some slides. Sherry. Okay. Yes, hopefully you can still see that okay. Yeah, I woke up on Monday, which was I think that was the climate change report, right? And it was also when my daughter came down with chicken pox in the morning. And so I sent a one-line email to my work being like, yeah, I'm not coming in for the week. And I just had kind of one of these moments where I was like, why am I looking 13 billion years ago to look at the first stars when, oh my God, maybe I should be fixing cancer or something. like, what am I doing with my life? Why should I be doing this? And so this 20 minutes is kind of what I just spent the last couple of hours thinking about before this presentation, in terms of how do I squish my thoughts on this into 20 minutes. So it's going to be a bit of a strange one, but yeah, just bear with me. So I didn't always want to be an astrophysicist. It's a weird field to have fallen into, but there you go. I grew up wanting to be an Egyptologist. I was desperate to find unopened tombs, like Lord Carter and Howard Carter and Lord Carnarvon, pictured here on the left, opening Tutankhamun's tomb. It's one of the best stories in the world, I think, let alone in Egyptology, chipping away, drilling a hole, Howard Carter holding up a light and Lord Carnarvon saying, what can you see? What can you see? And Howard Carter just saying, wonderful things, everywhere the glint of gold. This propelled me through my childhood and my teenage years, until I picked up a book. And I picked up a book on physics. And it was all about special relativity, which understandably I can also not cover in 20 minutes, but it's about the idea that, you know, you can move fast. The faster you move, the slower you age. And I was like, well, this is science fiction. I've got to go to university to learn about this. So I did. And then I got blown away by something else, and that was cosmology, which is the history of the universe. So instead of looking at the history of the human lifetime, I started to look a lot more at what happens, the Big Bang. Like, that's mad, right? The fact that the idea that the universe was squished all into this tiny point 38.8 billion years ago and then suddenly exploded, and here we are watching TV, and it's weird and I don't believe it, and yet all of the science, and there it is, I believe it. This is the power of science and data. You look at it and even the most preposterous idea becomes real, and this is magical to me. So what I do is radio astronomy, so we can look at the universe in all different kinds of light, There's lots of different kinds of light according to its wavelength. So we can think of light as like a wave on the water. It can be a very, very kind of long wavelength, or we can have these little ripples. And you have all of these different types of light, for example, radio light, which communicates over long distances, and this is how we get our radio signals. You've got your infrared for tracking criminals across the wherever field. You've got your UV light, which in CSI can, you know, pin down your killer, and you've got your X-ray light, of course, which can result in the diagnosis and everything of all of the illnesses that you might have. And we use all of these different types of light in daily life. You know, if you go to the doctor with a broken arm, you're going to be really miffed if they just look at your arm with visible light and go, yep, that's broken. You're going to want them to do an X-ray to figure out how to fix it. So to diagnose things in normal life, we are using all different kinds of light. And this is what we do in the universe as well when we're looking up with our telescopes. So here we've got a very average galaxy. It's the halo of light from all of the hundreds of billions of stars in it. You've got this dusty disk where you've got all of this star formation going on. You've got lots of stars in the background. It's a very nice picture. But when you add radio light, you get something more. You get an additional piece of information. And what this one shows is what we now see as standard out of a lot of galaxies, which are these gigantic radio lobes. They blow out from the galaxy, meaning that actually our definition of how big a galaxy is has got a lot larger. But also when we've looked at the science behind this, and we were like, what can cause that? That's really weird, which is the most exciting question in science. And it turns out that the only thing that can really power this kind of radio ejection is a black hole. And so suddenly we have a way of finding the most invisible thing in the universe, which is a black hole. And we can suddenly see where these might be in different galaxies. And we can use light in a really cool way. And this is what blew my mind at university and changed me again from kind of, I don't know, like useful physics to astrophysics, which is the fact that light, it might be really, really fast. It's about 300 million meters per second, but that's not infinite. And so, for example, if we're waving to our friend on the moon, that light takes 1.5 seconds to get there, and 1.5 seconds for the light from them waving back to get to us. It's only 2 seconds, 2.5 seconds. So we're fine, we're happy, we've had a useful social interaction, socially distanced. Then if we look at Mars, then that light takes 4 minutes to get there. And crucially, the light from Mars takes 4 minutes to get back to us. So that's a real delay. You know, we're a little bit annoyed because the friend we've waved at has taken 8 minutes and we basically just walked off. But this also means that we are seeing the light from Mars as it was 4 minutes ago. So we see Mars as it was 4 minutes ago. Okay, I mean, that's cool, but it's not the biggest delay. But now let's extend that to our nearest galaxy, Andromeda. So this takes 2.5 million years for our wave to get back to our alien friend, and 2.5 million years for it to get back, by which time we're not just sad, we're actually very dead. And so this isn't a great thing for when we're having social interactions, but wow, is it a good thing for astronomy? Because what we've just done is we found a way to look back in time. Because when we can tune in to the light that is coming from this particular galaxy, we are looking at that galaxy as it was 2.5 million years ago, which is pretty cool. Let's just, yeah, I have got this slide. And it works the opposite way around as well. So if there is some alien researcher who has the time and a telescope in Andromeda, and they decide to look at the third rock from the sun in this solar system, then they aren't seeing us talking here. What they're seeing is the Earth as it was 2.5 million years ago. So they're seeing one of the earliest ancestral branches of human existence, which is, yeah, I mean, this is what we use. This is what I do in daily life. I use this one fact. The further you look in distance, the longer, that light has taken to get to you. So the further back in time you are looking. And for me, I decided to look really far back. I decided to ask the question, along with a lot of other people, what was the universe like just after that preposterous idea, but entirely believable, let me underline that, it's true, the Big Bang? What happened afterwards? Because everything was pretty violent and energetic. You certainly couldn't form stars popped out with a Big Bang ready formed. It wasn't like that. You had to form it from the first building blocks. So how do we form those first stars and those first ever galaxies 13 billion years ago? So what I do is I tune into the light that has taken 13 billion years to get to us. Now, that takes a phenomenal telescope to be able to look back that far. And unfortunately, we can't do it with optical telescopes. The light is just too faint at that wavelength. And so instead, I use what has become my second passion, which is radio telescopes. And they just look at radio light. So the light from these stars, by the time it gets to us, it's been stretched by the expansion of the universe to about 2 meters wavelength, which is radio. And that makes it really easy for us to do. And why would we do this? You know, I was asking myself this 2 hours ago. I was like, and on Monday, why am I doing this? And the reason is it's because it's an unopened tomb, because we've taken lots of observations of our universal timeline. What we haven't got any data on is that first billion years after the Big Bang. This is a missing chunk of our timeline, and that really, really annoys me because I really, really like things to be complete. I like my collections of things to be complete, and so this really, really frustrates me. So that's one reason that I do it. But the other reason is that actually this isn't just kind of collecting the most common baseball cards for my collection. This is collecting the rarest, the most prized of cards, because these first stars, they're extinct practically, because they are so large. They get to be built so large in the early universe because of some very boring chemistry, and they get to be about 100 times the mass of our sun. And the bigger the star in our universe, the quicker it guzzles its fuel, which is hydrogen. So it lives very fast, dies young in only 1 million years. So if you think these things were formed about 13 billion years ago, they die, you know, in a blink of an eye cosmologically. And so they're all dead. You can't form them in the current universe because the universe has changed so much. And it's changed so much because of those first stars, which is the other reason I do this, because they're really important. Because in the early universe, they fused, they pushed together the lightest of elements, the hydrogen, the helium that was around. They pushed them together, they fused them. They made bigger and bigger building blocks. They made the building blocks that we need for planets, for galaxies, for us. You know, we are made of stardust, as Carl Sagan famously said. And when they died in only 1 million years, they threw all of this stuff out into the larger universe so that it could thrive. And it went from being empty and dark and boring and black to having this most incredible, diverse set of structures and, well, people. Yeah, so very quickly, because I know I am short on time. Oh yeah, no, that was it. So I've taken some like really quick notes that I decided to do a few minutes ago, because when I took this week off, I'm actually at my mum's house right now. So it was a last minute decision this morning, because I was like, right, I'm going to go to an antiques fair. And I thought, gosh, what am I going to buy? And pretty much the only thing that I bought was, let's see if I can see anything like that. Oh, I'm showing my screen. 1 minute. Okay, so you might not be able to see, but what it is a Victorian print of different cells in both plants and humans. And this was somebody in the Victorian age who thought, what are we made of? What is that made of? What is, everything made of? And I'm going to, sorry, not take pictures. I'm going to paint gorgeous, gorgeous things so that other people can learn about them. And they're all numbered and they don't come with the caption. So that's my night, because I'm going to hunt down every one of these little things and I'm going to find out exactly what they are. So, even in my week off, I have to know how things are built and I have to know how this universe is built. And so I use a radio telescope. I use what's called LOFAR, which are these little tiny, what we call bow tie antennas. There's 3,500 of these around Europe. We plug them all in together. It's the most simple technology. It's a piece of metal in a field. But when you put them all together and use the world's most powerful computers, then suddenly you can listen to that radio light from 13 billion years ago. There's a big race on to do this first detection. I'm not going to do this right now, but we tune into this light. And what we do to understand this era is that we take the temperature of the universe. And so the simplest measurement we can make is that when the universe goes from cold left to hot in the middle, that's when the stars are formed, because stars are hot. And so this is the most simple measurement we can do. And actually it was the Americans that won this one, University of Arizona. They managed to do the first detection of this kind. It's called EDGES, if you want to look it up. It was a fascinating thing. But the next thing we're looking at is called the Square Kilometre Array. And that's about 130,000 of these metal antennas, all plugged in with cable that would wrap twice around the Earth. And using the most powerful computers and the most intense collaboration of world governments in terms of science that has ever been. And it is going to take a while. People say, oh my God, well, I say it's been 10 years since, I started looking for this signal. Where is it? We've got one data point. Where is it? Why have we not got it yet? But I look back to my Egyptology. And I look back to Howard Carter's story, and he didn't just stumble across Tutankhamun's tomb. He spent 5 years. He spent 5 years meticulously gridding out where he thought things might be, and he looked and he looked and he looked. And his patron, Lord Carnarvon, eventually said, look, dude, you've spent all my money. You've had 5 years. You found diddly squat. Get out. At which point Howard Carter said, please, 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 one more season. What did they find? They found Tutankhamun's tomb. So you just got to keep looking. You just got to keep going. And along the way he did find things, and you find more questions, which is really important to me, to find more questions. I aim to start the day with a question, and I aim to finish the day with 5 more. That's how I know I've had a good day at science, and that's what we aim to do. We aim to do some incredible science with some incredible discoveries, and that's what keeps me going every day, actually. And that's why I do this. And it's because of another buddy was like, yeah, real life props are really amazing. So I was like, but I've got stars. I can't show stars. And so I'm showing you pictures that I got off my mum's wall. Which these are handprints from my 3 daughters, little, middle and big, and I follow their evolution every day. I watch them grow, and it's with an utter fascination that I see my universe, my personal universe. I'm getting, this is really like, I'm on the fly here and I'm like, oh my God, I'm so, yeah, they, you know, I see them grow and I see how they change in just this few years. And that missing billion years from our cosmological timeline is actually equivalent to missing every day of my daughter's life from the moment they're born to the first day they go to school. It's how much we're missing in the universe's evolution. So yeah, I want to find out. And I want to find out because my daughters, you know, on Monday, they wake up to a world where it is a bit difficult sometimes. You get climate change reports, you get chicken pox, you wear masks, you, which I love, by the way, that your group is like, you be vaccinated or get out. I mean, thank you for that. That's amazing. We do not have that much in England. They're like, wear a mask if you want to, it's cool, whatever. So yeah, thank you very much for that. But lastly, I just want to say that the reason, you know, that yeah, cool, I take the week off because my kid is sick and because I'm looking at them in summer holidays and I'm like, you know what, I'm going to spend a week with these amazing children and love them and play Lego and watch them. And but also I want to share the skies with them. I want to share that with them. And that's why I'm doing this every day and why I go into my office in the evenings, why I'll go into my office this evening and write. And that's why I wrote this book is I decided that, well, I mean, I saw that there was nobody talking about the first stars. I was like, but how? They're so interesting. and I really do believe that because I give talks normally 40 minutes long and people are like, oh, this is so interesting. So that's, you know, I want to share with them because there are awful things happening around us. It is difficult, but you know what, we can always look up. And that's why I love astronomy, is that you, I, anyone with no expertise at all can go out this evening and they can look up and we share the skies. And they are all of our skies, and we've got technology now where we can look further than the satellites that Elon Musk has put up, which is good. You know, I'm not getting into that conversation because they're good for internet for South Africa, you know, indigenous, but anyway, you know, we can look back, we can show people wonders away from us. And the reason we can do this is because it's technology actually built with people back down here. It's with scientific collaborations across governments, across politics, across religion. And I'm going to leave you with that, which is that when it gets difficult, look up. Thank you.